Welcome to Slothful Slumber, the podcast where we transform the vast knowledge of the internet into a gentle lullaby for your mind. I'm your host, Luna Dreamwell, and I'm here to guide you on a journey to tranquility through the soothing cadence of Wikipedia articles. Each episode will delve into the most wonderfully mundane and sleep-inducing topics, helping you drift off into a realm of serene dreams. So find your comfortable space, close your eyes, and let the dull hum of information carry you into a restful slumber. Now, let's embark on tonight's voyage of tranquil learning as we explore a topic so peacefully uneventful, it just might whisk you away to the land of dreams. This is part 2 of the Wikipedia article titled Earth. Let's continue reading about geophysical characteristics, tectonic plates. Earth's mechanically rigid outer layer of Earth's crust and upper mantle, the lithosphere, is divided into tectonic plates. These plates are rigid segments that move relative to each other at one of three boundaries types. At convergent boundaries, two plates come together. At divergent boundaries, two plates are pulled apart. And at transform boundaries, two plates slide past one another laterally. Along these plate boundaries, earthquakes, volcanic activity, mountain building, and oceanic trench formation can occur. The tectonic plates ride on top of the asthenosphere, the solid but less viscous part of the upper mantle that can flow and move along with the plates. As the tectonic plates migrate, oceanic crust is subducted under the leading edges of the plates at convergent boundaries. At the same time, the upwelling of mantle material at divergent boundaries creates mid-ocean ridges. The combination of these processes recycles the oceanic crust back into the mantle. Due to this recycling, most of the ocean floor is less than 100 million years old. The oldest oceanic crust is located in the Western Pacific and is estimated to be 200 million years old. By comparison, the oldest dated continental crust is 4,030 million years, although zircons have been found preserved as clasts within Eoarchean sedimentary rocks that give ages up to 400 million years, indicating that at least some continental crust existed at that time. The 7 major plates are the Pacific, North American, Eurasian, African, Antarctic, Indo-Australian, and South American. Other notable plates include the Arabian Plate, the Caribbean Plate, the Nazca Plate off the west coast of South America, and the Scotia Plate in the southern Atlantic Ocean. The Australian Plate fused with the Indian Plate between 50 and 55 million years. The fastest moving plates are the oceanic plates, with the Cocos Plate advancing at a rate of 75 millimeters per year, 3.0 inches per year, and the Pacific Plate moving 52 to 69 millimeters per year, 2.0 to 2.7 inches per year. At the other extreme, the slowest moving plate is the South American Plate, progressing at a typical rate of 10.6 millimeters per year, 0.42 inches per year. Internal structure. Earth's interior, like that of the other terrestrial planets, is divided into layers by their chemical or physical, rheological properties. The outer layer is a chemically distinct silicate solid crust, which is underlain by a highly viscous solid mantle. The crust is separated from the mantle by the Mohorovičić discontinuity. The thickness of the crust varies from about 6 kilometers, 3.7 miles, under the oceans to 30 to 50 kilometers, 19 to 31 miles, for the continents. The crust and the cold, rigid top of the upper mantle are collectively known as the lithosphere, which is divided into independently moving tectonic plates. Beneath the lithosphere is the asthenosphere, a relatively low viscosity layer on which the lithosphere rides. Important changes in crystal structure within the mantle occur at 410 and 660 kilometers, 250 and 410 miles, below the surface, spanning a transition zone that separates the upper and lower mantle. Beneath the mantle, an extremely low viscosity liquid outer core lies above a solid inner core. Earth's inner core may be rotating at a slightly higher angular velocity than the remainder of the planet, advancing by 0.1 to 0.5 degrees per year, although both somewhat higher and much lower rates have also been proposed. The radius of the inner core is about 1/5 of that of Earth. Density increases with depth, as described in the table on the right. Among the solar system's planetary-sized objects, Earth is the object with the highest density. Chemical composition. Earth's mass is approximately 5.97 by 10 to the 24 kilograms, 5,970 yig. It is composed mostly of iron, 32.1% by mass, oxygen, 30.1%, silicon, 15.1%, magnesium, 13.9%, sulfur, 2.9%, nickel, 1.8%, calcium, 1.5%, and aluminum, 1.4%, with the remaining 1.2% consisting of trace amounts of other elements. Due to gravitational separation, the core is primarily composed of the denser elements. Iron, 88.8%, with smaller amounts of nickel, 5.8%, sulfur, 4.5%, and less than 1% trace elements. The most common rock constituents of the crust are oxides. Over 99% of the crust is composed of various oxides of 11 elements, principally oxides containing silicon, the silicate minerals, aluminum, iron, calcium, magnesium, potassium, or sodium. Internal heat. The major heat-producing isotopes within Earth are potassium-40, uranium-238, and thorium-232. At the center, the temperature may be up to 6,000 degrees Celsius, 10,830 degrees Fahrenheit, and the pressure could reach 360 GPa, 52 million psi. Because much of the heat is provided by radioactive decay, scientists postulate that early in Earth's history, before isotopes with short half-lives were depleted, Earth's heat production was much higher. At approximately 3 Geyer, twice the present-day heat would have been produced, increasing the rates of mantle convection and plate tectonics, and allowing the production of uncommon igneous rocks, such as comatites that are rarely formed today. The mean heat loss from Earth is 87 milliwatt per square meter, for a global heat loss of 4.42 by 10 to the 13 watts. A portion of the core's thermal energy is transported toward the crust by mantle plumes, a form of convection consisting of upwellings of higher temperature rock. These plumes can produce hotspots and flood basalts. More of the heat in Earth is lost through plate tectonics, by mantle upwelling associated with mid-ocean ridges. The final major mode of heat loss is through conduction through the lithosphere. the majority of which occurs under the oceans, because the crust there is much thinner than that of the continents. Gravitational field. The gravity of Earth is the acceleration that is imparted to objects due to the distribution of mass within Earth. Near Earth's surface, gravitational acceleration is approximately 9.8 meters per second squared, 32 feet per second squared. Local differences in topography, geology, and deeper tectonic structure cause local and broad regional differences in Earth's gravitational field, known as gravity anomalies. Magnetic field. The main part of Earth's magnetic field is generated in the core, the site of a dynamo process that converts the kinetic energy of thermally and compositionally driven convection into electrical and magnetic field energy. The field extends outwards from the core, through the mantle, and up to Earth's surface, where it is approximately a dipole. The poles of the dipole are located close to Earth's geographic poles. At the equator of the magnetic field strength at the surface is 3.05 by 10 to the minus 5 Tesla, with a magnetic dipole moment of 7.79 by 10 to the 22 ampere per meter squared at epoch 2000, decreasing nearly 6% per century, although it still remains stronger than its long-time average. The convection movements in the core are chaotic. The magnetic poles drift and periodically change alignment. This causes secular variation of the main field and field reversals at irregular intervals, averaging a few times every million years. The most recent reversal occurred approximately 700,000 years ago. The extent of Earth's magnetic field in space defines the magnetosphere. Ions and electrons of the solar wind are deflected by the magnetosphere. Solar wind pressure compresses the day side of the magnetosphere to about 10 Earth radii and extends the night side magnetosphere into a long tail. Because the velocity of the solar wind is greater than the speed at which waves propagate through the solar wind, a supersonic bow shock precedes the day side magnetosphere within the solar wind. Charged particles are contained within the magnetosphere. The plasmasphere is defined by low-energy particles that essentially follow magnetic field lines as Earth rotates. The ring current is defined by medium-energy particles that drift relative to the geomagnetic field, but with paths that are still dominated by the magnetic field, and the Van Allen radiation belts are formed by high-energy particles whose motion is essentially random, but contained in the magnetosphere. During magnetic storms and substorms, charged particles can be deflected from the outer magnetosphere, and especially the magnetotail, directed along field lines into Earth's ionosphere, where atmospheric atoms can be excited and ionized, causing the aurora. Orbit and rotation. Rotation. Earth's rotation period relative to the Sun, its mean solar day, is 86,400 seconds of mean solar time, 86,400.0025 SI seconds. Because Earth's solar day is now slightly longer than it was during the 19th century due to tidal deceleration, each day varies between 0 and 2 milliseconds longer than the mean solar day. Earth's rotation period relative to the fixed stars, called its stellar day by the International Earth Rotation and Reference System Service, IERS, is 86,164.0989 seconds of mean solar time, UT1, or 23 hours, 56 minutes, 4.09 989 seconds. Earth's rotation period relative to the precessing or moving mean March equinox, when the Sun is at 90 degrees on the equator, is 86,164.0905 seconds of mean solar time, UT1. 23 hours, 56 minutes, 4.0905 seconds. Thus, the sidereal day is shorter than the stellar day by about 8.4 milliseconds. Apart from meteors within the atmosphere and low-orbiting satellites, the main apparent motion of celestial bodies in Earth's sky is to the west at a rate of 15 degrees per hour, equal sign, 15 arcseconds per minute. For bodies near the celestial equator, this is equivalent to an apparent diameter of the Sun or the Moon every 2 minutes. From Earth's surface, the apparent sizes of the Sun and the Moon are approximately the same. Orbit. Earth orbits the Sun, making Earth the third closest planet to the Sun and part of the inner solar system. Earth's average orbital distance is about 150 million kilometers, 93 million miles, which is the basis for the astronomical unit and is equal to roughly 8.3 light minutes or 380 times Earth's distance to the Moon. Earth orbits the Sun every 365.2564 mean solar days, or one sidereal year, with an apparent movement of the Sun in Earth's sky at a rate of about 1 degree per day eastward, which is one apparent Sun or Moon diameter every 12 hours. Due to this motion, on average, it takes 24 hours, a solar day, for Earth to complete a full rotation about its axis so that the Sun returns to the meridian. The orbital speed of Earth averages about 29.78 kilometers per second, 107,200 kilometers per hour, 66,600 miles per hour, which is fast enough to travel a distance equal to Earth's diameter, about 12,742 kilometers, 7,918 miles, in 7 minutes, and the distance to the Moon, 384,000 kilometers, 239,000 miles, in about 3.5 hours. The Moon and Earth orbit a common barycenter every 27.32 days relative to the background stars. When combined with the Earth-Moon system's common orbit around the Sun, the period of the synodic month, from new moon to new moon, is 29.53 days. Viewed from the celestial North Pole, the motion of Earth, the Moon, and their axial rotations are all counterclockwise. Viewed from a vantage point above the Sun and Earth's North Poles, Earth orbits in a counterclockwise direction about the Sun. The orbital and axial planes are not precisely aligned. Earth's axis is tilted some 23.44 degrees from the perpendicular to the Earth-Sun plane, the ecliptic, and the Earth-Moon plane is tilted up to plus or minus 5.1 degrees against the Earth-Sun plane. Without this tilt, there would be an eclipse every 2 weeks, alternating between lunar eclipses and solar eclipses. The Hill sphere, or the sphere of gravitational influence of Earth, is about 1.5 million kilometers, 930,000 miles, in radius. This is the maximum distance at which Earth's gravitational influence is stronger than the more distant Sun and planets. Objects must orbit Earth within this radius, or they can become unbound by the gravitational perturbation of the Sun. Earth, along with the solar system, is situated in the Milky Way and orbits about 28,000 light-years from its center. It is about 20 light-years above the galactic plane in the Orion Arm. Axial tilt and seasons. The axial tilt of Earth is approximately 23.439281 degrees, with the axis of its orbit plane always pointing towards the celestial poles. Due to Earth's axial tilt, the amount of sunlight reaching any given point on the surface varies over the course of the year. This causes the seasonal change in climate, with summer in the northern hemisphere occurring when the Tropic of Cancer is facing the sun, and in the southern hemisphere when the Tropic of Capricorn faces the sun. In each instance, winter occurs simultaneously in the opposite hemisphere. During the summer, the day lasts longer, and the sun climbs higher in the sky. In winter, the climate becomes cooler and the days shorter. Above the Arctic Circle and below the Antarctic Circle, there is no daylight at all for part of the year, causing a polar night, and this night extends for several months at the poles themselves. These same latitudes also experience a midnight sun, where the sun remains visible all day. By astronomical convention, the 4 seasons can be determined by the solstices, the points in the orbit of maximum axial tilt toward or away from the sun, and the equinoxes, when Earth's rotational axis is aligned with its orbital axis. In the northern hemisphere, winter solstice currently occurs around the 21st of December. Summer solstice is near the 21st of June. Spring equinox is around the 20th of March, and autumnal equinox is about 22 or the 23rd of September. In the southern hemisphere, the situation is reversed, with the summer and winter solstices exchanged and the spring and autumnal equinox dates swapped. The angle of Earth's axial tilt is relatively stable over long periods of time. Its axial tilt does undergo nutation, a slight, irregular motion with a main period of 18.6 years. The orientation, rather than the angle, of Earth's axis also changes over time, precessing around in a complete circle over each 25 800-year cycle. This precession is the reason for the difference between a sidereal year and a tropical year. Both of these motions are caused by the varying attraction of the sun and the moon on Earth's equatorial bulge. The poles also migrate a few meters across Earth's surface. This polar motion has multiple cyclical components, which collectively are termed quasi-periodic motion. In addition to an annual component to this motion, there is a 14-month cycle called the Chandler wobble. Earth's rotational velocity also varies in a phenomenon known as length of day variation. In modern times, Earth's perihelion occurs around the 3rd of January, and its aphelion around the 4th of July. These dates change over time due to precession and other orbital factors, which follow cyclical patterns known as Milankovitch cycles. The changing Earth-Sun distance causes an increase of about 6.8% in solar energy reaching Earth at perihelion relative to aphelion. Because the southern hemisphere is tilted toward the sun at about the same time that Earth reaches the closest approach to the sun, the southern hemisphere receives slightly more energy from the sun than does the northern over the course of a year. This effect is much less significant than the total energy change due to the axial tilt, and most of the excess energy is absorbed by the higher proportion of water in the southern hemisphere. Earth-Moon system. Moon. The Moon is a relatively large, terrestrial, planet-like natural satellite with a diameter about 1/4 of Earth's. It is the largest moon in the solar system relative to the size of its planet, although Charon is larger relative to the dwarf planet Pluto. The natural satellites of other planets are also referred to as moons after Earth's. The most widely accepted theory of the moon's origin, the giant impact hypothesis, states that it formed from the collision of a Mars-sized protoplanet called Theia with the early Earth. This hypothesis explains the moon's relative lack of iron and volatile elements, and the fact that its composition is nearly identical to that of Earth's crust. The gravitational attraction between Earth and the moon causes tides on Earth. The same effect on the moon has led to its tidal locking. Its rotation period is the same as the time it takes to orbit Earth. As a result, it always presents the same face to the planet. As the moon orbits Earth, different parts of its face are illuminated by the sun, leading to the lunar phases. Due to their tidal interaction, the moon recedes from Earth at the rate of approximately 38 millimeters per year, 1.5 inches per year. Over millions of years, these tiny modifications and the lengthening of Earth's day by about 23 microseconds per year add up to significant changes. During the Ediacaran period, for example, approximately 620 million years, there were 400 plus or minus 7 days in a year, with each day lasting 21.9 plus or minus 0.4 hours. The moon may have dramatically affected the development of life by moderating the planet's climate. Paleontological evidence and computer simulations show that Earth's axial tilt is stabilized by tidal interactions with the moon. Some theorists think that without this stabilization against the torques applied by the sun and planets to Earth's equatorial bulge, the rotational axis might be chaotically unstable, exhibiting large changes over millions of years, as is the case for Mars, though this is disputed. Viewed from Earth, the moon is just far enough away to have almost the same apparent size disk as the sun. The angular size, or solid angle, of these two bodies match because, although the sun's diameter is about 400 times as large as the moon's, it is also 400 times more distant. This allows total and annular solar eclipses to occur on Earth. Asteroids and artificial satellites. Earth's co-orbital asteroids population consists of quasi-satellites, objects with a horseshoe orbit, and Trojans. There are at least 5 quasi-satellites, including 4 69219 Kamo-Oelewa. A Trojan asteroid companion, 2010 TK7, is librating around the leading Lagrange triangular point, L4, in Earth's orbit around the Sun. The tiny near-Earth asteroid 2006 RH-120 makes close approaches to the Earth-Moon system roughly every 20 years. During these approaches, it can orbit Earth for brief periods of time. As of September 2021, there are 4,550 operational human-made satellites orbiting Earth. There are also inoperative satellites, including Vanguard 1, the oldest satellite currently in orbit, and over 16,000 pieces of tracked space debris. Earth's largest artificial satellite is the International Space Station,